Hey AP, in this video we are going to look at Gibbs free energy. So in yesterday's video we talked about enthalpy and entropy, and we said that there's one more factor involved with our thermodynamics, and that's Gibbs free energy, which is our delta G. So we're going to take a look at that today. So first off, why do chemical reactions even occur? Well, they occur because of free energy. And free energy has the formula. Well, first off, it's shown by delta G, and we get that from looking at the heat of reaction, or delta H, minus the temperature times the change in entropy. And this is another formula that is on your formula sheet, so that is shown here. Okay, and again, we can see we've got temperature. For our R here, this is our gas law constant, this is our constant, and we'll look at this in a little bit. But we've got delta H, T, and delta S. So we need to be able to determine if a reaction is considered spontaneous or not. Remember, spontaneous means that a reaction is going to occur without having to put more energy into it to force it to occur. And if a reaction is spontaneous or not, that has to do with our value of delta G, where delta G represents whether or not it's spontaneous or not. So we can have the work, W max, which is the free energy available to do useful work. And we say that delta G is equal to our maximum work available. We have our delta H, which is the energy available for us to do that useful work. And then negative T delta S represents the energy that can't be harnessed due to useful work. So stuff that we can't harness here. So if we have our delta G, we say that determines spontaneity. Well, if our delta G is less than 0, that is a spontaneous reaction, and it moves in the forward direction. If my delta G is positive or greater than 0, that is a non-spontaneous reaction. As it is written, but it means that it would be spontaneous in the reverse direction. If delta G is 0, that means that we are at equilibrium. Now, because of our formula here, we can look at our delta H values and delta S values and get an idea of whether or not our system is going to be negative and spontaneous for delta G or positive and non-spontaneous for delta G. So let's take a look. If I have a negative delta H and a negative delta S, so I have a delta H less than 0 and a delta S less than 0. So if I have a negative value minus another negative value, well, two negatives cancel out, which would make this overall be positive, which means that if my delta S is too big, or my temperature actually is too big, that's going to force this overall to be positive, which would mean a positive delta G. So if both my values are negative, I am only spontaneous at low temperatures. Okay. Because that way I am still staying in the negative range. If I have a negative delta H, so I have a negative value, and then I'm subtracting another value from my negative value, that's just going to make it more negative. And if I'm just making it more negative, that's guaranteeing it to be negative all the time, which means that a negative enthalpy and a positive entropy is always going to be spontaneous. Okay. Well, what if I have an endothermic reaction or a positive delta H? If I have a positive delta H here, and I'm subtracting a negative delta S, so positive minus a negative, that's going to make this overall positive positive plus positive is always positive. So that means these are never going to be spontaneous because it's always going to be positive. Okay. But what if I have a positive delta H and then I'm subtracting some amount of entropy, which is also positive? Well, if this value can get big enough, can it get bigger than my delta H value and overcome it? Well, then overall I'm going to have a negative value. So these are only spontaneous at high temperatures. Okay. So if I have negative and positive, always spontaneous, positive and negative, never spontaneous, and then only at low and only at high. So how do we get these delta G values? Well, we can get them from our formation, our Gibbs free energy of formation values, and we can use this equation here of our delta H minus T delta S. So let's take a look at how those work. We can have our standard free enthalpy or free energy of reaction, which is our delta G of our reaction. It's the free energy change for a reaction when it occurs under standard state conditions. So those standard states are coming back again. We can have the standard free energy of formation, and that occurs when we are making 1 mole of the compound formed from its elements in their standard states. And if just like with enthalpy, delta G of any element in its standard form is also 0. And we'll see that in our chart as well. So remember, again, we're getting these values from our chart, which is in the front of our packet. And we can see those here. We have delta H, delta G. So if I'm looking at something like carbon, in its standard state, 0 for delta H, and also 0 for delta G. So what is the standard free energy change for the following reaction at 25 degrees Celsius? So if I want the energy change at 25 degrees Celsius, let's take a look. And that means I'm just looking at how does it change throughout my reaction. And we'll note that this is just like our standard free entropy change, standard free enthalpy change, standard free energy change, all here. Products minus reactions, the sum of them. So we need to plot our values from our chart. I guess we can also put in, so our delta G naught is the sum of our delta G of our products minus the sum of our delta G of our reactants. Okay, remember that N has to do with our moles that we have from our equation. So from our chart, we need calcium carbonate, negative 1129. Calcium oxide, negative 604. And carbon dioxide, CO2, negative 394. And also important to note, our units on delta G are the same as delta H, but different from S, so kilojoules per mole. So if I want my delta G of my reaction, sum of my products, this is a 1, so negative 604 plus a negative 394 minus sum of my reactants, negative 1129, and I get an answer of 131, my units, kilojoules per mole. That's a positive value. So at 25 degrees Celsius, is this spontaneous? No, not spontaneous because we have a positive delta G. Okay, but could we have a situation or a temperature in which we do have it be spontaneous? Well, that's something that we can also see. So for the above reaction, we know that our delta H is 177.8. That doesn't favor spontaneity. Our delta S is positive, though, so that does favor spontaneous reaction. So if we look back, we've got a positive delta H and a positive delta S. Positive delta H, positive delta S, only spontaneous at high temperatures. Well, how can we figure out what that is? Well, we know that our delta G to be spontaneous is where it is less than or equal to 0. Okay, so what if I say, well, let's say delta G is equal to 0, because then anything more than that would be, or less than that would be our, it would be a spontaneous reaction. So for my formula, delta G, delta H minus T delta S, if I'm saying that I want to find temperatures that are at or above this that I need to have it be negative. So I'm going to say my delta G is 0. I know my delta H, 177.8, minus the temperature, that's what I'm looking for. And then one thing to note, this is in joules per Kelvin. So if I put that in kilojoules, that's 0.1605 because there's 1,000 joules in a kilojoule. So 1605. All right. I'm going to add this to both sides. So temperature 0, 1605 is 177.8, and divide this away. It's my temperature 177.8 over 0.1605, and I get a temperature of, in my notes, 1107.8 Kelvin, which Kelvin doesn't mean a hot mess to us, a lot to us. So putting that in Celsius, 835 degrees Celsius. So if I want this to be a spontaneous reaction, I need the temperature to be at or above 835 degrees Celsius. Then it'll be spontaneous. It's a pretty hot reaction, but we can get there. All right, what about phase transitions? Well, we know in a phase transition that those are always at equilibrium. Okay, and if these are at equilibrium, all of these are at equilibrium. That means that at a phase change, my delta G is equal to 0, because phase changes happen at equilibrium. We also know that they're temperature dependent because equilibrium only happens at certain temperatures. So based on knowing that at equilibrium, delta G is 0, and a phase change is at equilibrium, we can determine the boiling point or the evaporation point of any substance, really, so long as we know our delta S and our delta H, because we're saying delta G is 0. So if I were, again, delta G, delta H minus T delta S, if delta G is 0, that means that really, and if I'm looking for the temperature, that means my temperature, when I rearrange this equation, temperature would slide over, so I'd add it to both sides, and then divide off by my delta S. So temperature is delta H over delta S. And again, we want these to be in the same unit, so both in kilojoules, so this will be 0.1093 kilojoules per mole Kelvin. So we have our delta H, 40.62 kilojoules per mole, divided by our delta S, 0.1093 kilojoules per mole Kelvin. Our units work out because kilojoules cancel out kilojoules, moles and moles. We're left with 1 over Kelvin, which brings Kelvin up. So my number that I get is 371.6 Kelvin, which in Celsius we subtract 273, 98.6 degrees Celsius, okay, which is pretty close given what we know about water. So we can get that kind of information from our thermodynamic data. So let's summarize what we know about equilibrium and what we know about delta G. So we know to have a spontaneous reaction, we need to have a delta G that is negative. That's a negative delta G. And if we're looking at, well, let's go through those. And at equilibrium, we know our delta G has to be 0. And to be non-spontaneous, we have a positive delta G. Well, if we have Q and K, remember Q is our reaction quotient for a reaction at a certain time, and K is at equilibrium. We know that if we have a spontaneous reaction or a reaction that moves forward, we know that Q is less than K, which makes a forward reaction happen. If we're at equilibrium, we know that Q is equal to K. And if we're of a non-spontaneous reaction, in other words, a reaction that really should proceed in the reverse direction, we know that Q is greater than K. And that makes a reverse reaction. Okay, so based off of that, we have another formula that we can use to look at delta G values. And we are going to say that for this situation, again, because we're looking at standard state conditions, and at standard state conditions, remember that at equilibrium, we're looking at equilibrium, Q is K and delta G is 0, we can then say that even though experimentally delta G is delta G naught plus RT ln of K, well, if it's at equilibrium, delta G is 0, so we can get rid of that, goes to 0, and we can have delta G was RT ln of K using K because we're at equilibrium. And again, this is another one of your formulas that is in your chart here, this negative RT ln of K. Also important to note that this R is our gas constant, 8.314 joules per mole Kelvin. Okay. So let's take a look at what we can find out using this formula when we have things at equilibrium. So we have the formation of nitrogen monoxide from nitrogen oxygen gas in a reaction that strongly favors the reactants. So if it strongly favors the reactants, that means I really have a delta G that's positive, which means that I also have strongly favors reactants, that my Q is greater than K for the situation because it hangs out over here on that left-hand side. Now, the actual concentrations of each gas would be difficult to measure, so the KEQ for the reaction can be more easily calculated from the delta G, which is equal to 173.4 kilojoules per mole. We also know our R value, and we're told the temperature that we're at, 25 degrees Celsius, so we know our temperature in Kelvin. Well, if I want to find my equilibrium constant, KEQ, I can do that for my equation, delta G equals negative RT ln of K. And now we're using the natural log, different than our regular logs. So let's go ahead and plug in our values. So you got 173.4 equals negative R, 8.314, temperature 298, ln of K. When I move these over, I get negative 69.99 equals ln of K. Now to reverse our natural log, we take a look on our calculators. We have our natural log button here, and the opposite of that is our e to the x. So that's what we'll use to get rid of our natural logs. We're going to do second ln to get e to the x. Looks like that. And then type in negative 69.99. And that's going to give us our opposite of our natural log. So 4.02. So this is e to the. So K equals 4.02 times 10 to the negative 31. And this number makes sense because this negative 31 is super small, which tracks with the fact that we said it strongly favors the reactants. We know that a very small K value means that we really hang out on the left-hand side of our reaction. Well, what if I know my solubility product constant, my K, of lead-2 iodide, and I know my temperature? Can I also calculate delta G for a certain system? And we can do that too. So again, we have our delta G is equal to negative RT ln of K. We can figure out, does this happen spontaneously? Does it not? So we can do that instead of having to look at Q and K values together. So we plug in minus 8.314, temperature 298, natural log 1.4 times 10 to the negative 8, which is just our KSP value. We find here that my delta G is 44804.9. This is in joules because the units on this guy are joules. So we could put that into kilojoules by dividing by 1,000, so 44.8 kilojoules per mole. But we've got a positive value here. So is this spontaneous? No, this doesn't just naturally dissolve in water. However, we could force it, probably at different temperatures. We could figure that out doing one of the other calculations. But we can see that my delta G value for this is my positive value of 44.8. And that are the end of our notes.